Hello everyone, I'm Xiaoxue Zhang from UC Santa Cruz. The paper I present today is Scalable Decentralized Routing for Blockchain Payment Networks. This work was done in cooperation with Shouqian, and Chen, who are also from UCSC. Blockchain is a hot topic these days. However, the limitations are also obvious. For example, Bitcoin at the moment manages around 7 transactions per second, while some centralized payment hubs like Visa and MasterCard could process more than 47,000 transactions per second. We can see the difference here. Here are some limitations of blockchain. Bitcoin will take around 10 minutes to generate a block, so it's hard for instant payments. And the second problem is scalability. The most popular consensus algorithm proof of work, it is a time and resource consuming process. And every time when new block arrives, all the nodes in the networks have to process it and update the state of the blockchain, which lead to the low transaction rate. And the third problem is micropayments. Fees render micropayment transactions unviable on the networks. So one solution to improve the blockchain is blockchain payment networks or off-chain networks. The main idea is to execute payment off-chain. In a nutshell, we have two users, and they could build a channel that has a certain total capacity in this channel. Then they could conduct transactions with each other directly without having these transactions being packed into the blockchain. For example, here Alice and Bob could make some transactions while the channel between them directly. So here are some properties of these payment channels. First, payment channels could only exist between two users, and sharing a channel reflects some levels of trust, which means that only if you trust someone, then you will build a channel with this node. And second, the users will only interact with blockchain in these two situations: channel opening and shutting down, or when the users have some disagreement on the channel state. And the users do not need to broadcast all transactions to every node in the network. As I said before, the channel could only exist between two users. So what if when two users want to make some transactions, but they don't trust each other, so they don't have a channel between them? Such as the Alice and Dave here, they want to make some transactions, but there's no direct link between them. So the solution is that they could make some transactions while some intermediate nodes, such as the Bob here. They first pay Bob $4 and then Bob pay Alice $4. This is how multi-hop channels work. So the problem is how to do routing for the senders and receivers, how to find a path between them. Here are some current routing solutions of overlay networks. The first, centralized routing that every node knows the network topology. However, it needs massive control message to be broadcast, and actually it will lead to privacy leakage of the global topology. And the second, landmark routing. Landmarks may be congested by massive traffic and become system bottleneck. For structured overlay networks such as distributed hash table, in DHT it forces each node to maintain links to designated nodes and use the links for routing. Actually, it's not applicable in off-chain networks because the node may not trust the designated nodes. And for gossip routing, it does not guarantee success of finding impasse, so it's also not applicable in off-chain networks. Here are the challenges of our work. The first is that we are aimed to design a scalable routing solution for off-chain networks, and we want it to be fully decentralized. There's no central authority or landmarks. The simple thought is to use greedy routing. However, it is well known that simple greedy routing does not always succeed because it may be stuck at a local minimum node. But multi-hop Delaunay triangulation, or MDT, is a geography routing protocol providing guaranteed delivery with low routing stress. So our thought is to use MDT in our routing for blockchain payment networks. So let's first start with Delaunay triangulations. For a given set of nodes S in a 2D space, the Delaunay triangulation, the dt of S, is defined as a triangulation such that no fourth node in S is inside the circumcircle of any triangle, such as this graph here. And two nodes are called dt neighbors if they share an edge in dt graph, and this edge is called dt edge. The left graph shows part of the topology of the networks. Here the edge is the physical link, which means that the node could communicate directly through this link. So the physical neighbor of U is A, B, C, and D here. And the graph on the right side is part of the Delaunay triangulation of S. And those edges are DT edges. So the DT neighbor of U is A, B, and C here. It has been proved that greedy routing on the DT edge, assuming all DT neighbors are connected, are always success to find the destinations. But the problem is, it's not always that DT neighbors are unconnected, such as, what if this link do not exist? Then C is not the physical neighbor of U, but C is still the DT neighbor of U. One improvement of the Delaunay triangulation is multi-hop Delaunay triangulations. Here is an example. The graph here shows the topology of a network, and all the solid line, including the red solid line and black solid line, shows the physical links of this graph, and all the red line, including the solid red line and the dashed line, shows the Delaunay triangulation of this graph. In this multi-hop Delaunay triangulation, the neighbors are defined as, first, the physical neighbors, those nodes that are directly connected, and second, those DT neighbors that is multi-hops apart and can communicate via a virtual links. For example here, A and D, they are DT neighbor, but they are not physical neighbor. However, they could communicate via a physical path that is A to B and then to C and to D. Then we can say that they are multi-hop DT neighbors. They are MDT neighbors because they could communicate via a virtual links. It has been proved that greedy routing always succeeds to find the destinations on an MDT, and it achieves low routing stretch from efficient forwarding of packets at local minimum. Here I show how we do MDT routing in off-chain networks. First, we need to assign the coordinate for each node. We could simply use multi-dimensional scaling to assign the coordinate, and for each node, they only need to maintain the coordinate of itself and its physical neighbors. In here, I show the forwarding protocol as a certain node U. The first step to do is you need to search all its physical neighbor to find out if there's any node that is closer to the destinations. If it finds that its physical neighbor V is node that closer to the destinations, then it will transmit to V. However, if U itself is the closest node to the destination are among all its physical neighbors, then we will go to the second step. It will search for all its DT neighbors, including those DT neighbors who is not its physical neighbors but have a virtual link to it. If we find that the DT neighbor V is closer to the destinations, then it will transmit to the next hop on the path from U to V. If the two steps are both false, then U is already the closest node to destinations. I will show examples here. For example, the sender is D and the receiver is H. Now, starting from D, we want to find a path from D to H. First, D will search all its physical neighbor to find the node that is closer to the destinations. It's easy to find that there is a physical neighbor C that is closer to H. Then the next hop is C. Now for C, it will first searching for all its physical neighbors. However, it finds that it's already the closest node among all its physical neighbor to H. Then it will go to the second step. It will search for all its DT neighbors. And it finds that the DT neighbor A is the closest node to H among all its neighbors. Then it needs to transmit to A. However, there's no physical link between C and A, and we know that there is a virtual link from C to A while C to B to A. So C will transmit to B, which is the next hop on the path from C to A. And here's how it works. And now we go to the evaluation part of our system, Webflow. In the evaluation part, we aim to answer these three questions. How well does the Webflow routing perform? How effective is the routing algorithm under different number of nodes? How does the number of channels per node, average degree, affect the performance? And we do some comparisons using the repo network topology, and we compare our Webflow with shortest path, speedy murmur, and silent whisper. In our simulations, we set nodes from 1,000 to 200,000 nodes. Here are the results of our evaluation. The first figure shows the hop delay of our system, which is the average length of path. And second is the processing delay of our system, which is the time it takes to find a path. The figure shows that even if the number of nodes achieve 20,000, we could still achieve hop delay below 8 and processing delay below 2.5 milliseconds. And when comparing our system Webflow with other routing algorithms, the result shows that the Webflow is much better than speedy murmur and silent whisper. When comparing with shortest path, the result shows that Webflow only takes slightly longer delay in hop counts than shortest path. Our future work will go into capacity and concurrency, which means that when one or more probe operations or routing operations aim to use the same channel. And we'll also consider privacy, including sender privacy, receiver privacy, and value privacy. Here's the summary of our work. We built Webflow, which is an MDT-based routing system. It achieved scalable and decentralized routing, and it could support large and dynamic blockchain payment networks. It achieved low delay, low probing overhead, and guaranteed success of finding path. Thank you, everyone. Is there any questions?